Welcome back to this NPTEL online certification course of molecular rearrangement and reactive intermediates. In the last couple of classes, I was talking about the single electron transfer reagents. So that can be used for generation of a radical, and now this radical species can be take part in a pinnacle coupling or a Barbier reaction. So in the today's class, I am going to focus on the samarium because there are several important reactions about the samarium. I am going to talk about how the samarium iodide was synthesized, and what are the different reaction using samarium iodide. So first thing I am going to talk about the alkyl halide reduction reaction, then the pinnacle reaction, of course the ketone aldehyde reduction reaction, cyclization. So and then there will be some Grignard or the Barbier reaction, Reformatsky reaction, and I am going to talk about the aldol reaction at the end. So first thing, I think the Kagan group actually developed the method how to generate the samarium iodide. Okay. So the samarium iodide is a very important single electron, so it's a one electron or a single electron reducing agent. It can be generated starting from samarium. Okay, if you use this 1,2-diiodoethane, it will generate the SMI3, which is going to react with the samarium to form the SMI2. And there will be one important thing is solvent play a very important role. So solvent will make a coordinated complex with the samarium. So once you make them also, you have to use the THF in the reaction. So actually samarium iodide is a green solid, okay, but once it is combined with the THF, you are going to see a very deep blue color. So that blue color actually indicate that yes, you got to the samarium iodide which is now ready for the reaction. So what is that mean of the color? That is kind of showing that it is a slightly ionized samarium has formed. That means you already have electron density density there, which can now take part in the different type of chemical transformations. So there are different type of reduction reaction using samarium iodide, and we can talk about the functional group reduction. That means you start with different functional group like alkyl halide, carbonyl group, then corresponding alkyl nitro. So that can be reduced because having so it has a wide range of reduction potential. So this is the reduction potential using THF minus 1.33 electron volt, but this is not the reduction potential of samarium iodide. It can go up to 2.6 or even up to 3 electron volt if you change the additives and the different solvents. So it not only go for the functional group reduction, that can be also done with other different type of reducing agent or other different single electron transfer. But the important thing is this can participate in a very important type of reaction like pinnacle reaction. I am going to talk about Barbier reaction, Reformatsky reaction, and some of the most importantly some of the intramolecular radical cyclization. That is still nowadays also you will see a publication where this samarium iodide is still very useful for formation of the carbon-carbon bonds. First I am going to talk about the different type of additives. So of course samarium forms a complex with the THF, as you guys see samarium iodide a THF complex. Now people have also used different type of additives, because what happened once the additives, so there are different type of additives. So let's talk about them. There are one is the Lewis bases. One of the important one which is often used with the samarium is the HMPA, hexamethyl phosphoric triamide. So these are the electron donor ligand or a chelating ligand which forms some sort of a complex with the with the samarium. I am going to also talk about them in the later slides. Then there are other type of additives called the proton donor. So they become last 2 decades this proton donor become very popular in the samarium reaction. So they can be water, alcohol, okay, or the glycols, all they can be used as a proton donor. And people have found out using water they can found there is some sort of a proton couple. So there is some sort of PCET also happening. I am going to explain also them in the later on. There is something called the inorganic additives that could be lithium bromide or lithium chloride. Again this can react with samarium iodide, samarium bromide, which can form more solubility in the THF. So that can help with the solubility. Again the solvent can play a very important role, as I mentioned, because generally you can see mostly the ether type of solvent was used. But again if you can add some of the other solvent, the reactivity has changed because there is a change in the reduction potential of the samarium iodide. Okay. So I think the high affinity proton donor promote the proton couple electron transfer, as I mentioned at the beginning, if you use the water or the corresponding alcohols. So, the most important fact is in these additives there are some of the additives like lithium bromide have help with the solubility, but other additives HMPA or the the protic additives, they actually form some sort of a complex with the samarium iodide, so that there is a change in the redox potential. That is the important factor. So, first thing I am going to talk about the reduction of alkyl halide here. So, first if you have a Rx and the samarium iodide, it is going to form this R dot, it is through a single electron transfer, samarium will be converted to the samarium 3 and it is going to form the R dot, which can again take another samarium iodide to form this RSM3, which can finally take some proton to get to the RH, or it can abstract so there could be a hydrogen atom abstraction from the solvent to form the RH, or there is a process called a radical recombination to form a dimer. Again you can see here, if you are doing this reaction, then if you have a X equal to iodo versus bromo versus chloro, what is happening? As the carbon halide bonds energy is getting increased, your reaction is becoming slower and slower. Okay, that is kind of understandable, that your bond dissociation energy, so the bond energy getting decreased, at the same time the corresponding the reduction time is getting increased. Again very similar things here. And now the thing is, if you use HMPA, what is happening here? So, HMPA is making a huge difference, because at the beginning you have seen you are for X equal to bromo you are 48 hours, chloro even no reaction. But here once you use HMPA, we can see in case of bromo and chloro, which was almost it is a very long reaction, now under 10 minutes or 8 hours these reactions are possible. What is happening here? Once you add HMPA, this changes the redox potential, that is allowing you to now reduce this carbon chlorine bond much faster. So, this is a complex. So, you can see there are 5 THF unit with the samarium iodide. So, this is samarium in the center, there is 2 iodine here with the purple color, and there are THF units here. So, this samarium iodide THF complex getting, first it is forms in terms of THF, but once you add this HMPA, it actually dissociates this complex. So, this is the, so it actually make it's kind of form aggregation at the beginning with the THF, but HMPA kind of break this aggregation. So, that is a very important part of the HMPA. So, it breaks the aggregation, makes the samarium free from the THF. So, that means samarium now has the chance to coordinate with this some of the like with oxygen of the carbonyl or other things. So, that means that can remove some of these THF units and also make a change in the redox potential. So, this is in the THF, that is in the HMPA, which I was telling in the previous slide. And again that is also depend how much equivalent of HMPA you are using. It is not that if you use 1 equivalent of HMPA you will achieve to this redox potential. So, you know what is going to happen if you have a samarium iodide in THF, and now if you are adding HMPA 1 equivalent after another equivalent, you are seeing a change in the redox potential, but after a certain amount you will not see. So, there will be saturation. Again we are seeing here in this reaction, once you are doing the reduction here, the samarium, it is going to reduce the corresponding alkyl halide to the corresponding RH after it is getting to the proton from the corresponding if you have a proton source. Okay. So, now I am going to talk about the pinnacle reaction versus the reduction. So, if you have a carbonyl group here, what is happen? First thing, once you have a carbonyl group here and you have a samarium iodide, samarium act as a single electron transfer agent. That means now it is going to end up making this samarium ketyl radical. That is the very important species. Okay. So, you will see lot of reaction happening from this samarium ketyl radical, which is happening after the reduction of the carbon species. First thing is it can form this species here. You can see that it can go for another molecule of this, can form this type of, so both of the molecules, 2 of the molecule can form this species, can take 2 of the samarium unit. So, after that it can take it can convert here. After, so how this is conversion happening? From there you can see, from here there is a radical species here which is generating, that can be also taken with the samarium in case of samarium iodide, which can be after the protonation it can form the corresponding alcohol, or from here it can also form the corresponding pinnacle. So for the pinnacle, what is going to happen? These two radical can go for a radical recombination. If there is a radical combination happening, recombination happening, it can form the pinnacle. But if it is taking another summary amide and going for a protonation, then it is forming this corresponding alcohol. So there is a two possibility. It can go for a reduction or it can go for a pinnacle coupling. I am going to show you some of the example here. So you have a carbonyl group and you have a ester here. So these are some of the example of intramolecular reaction. So now you have learned about, I think I have already talked about that if you are forming a radical species, then if you have a double bond there, that can participate in an intramolecular radical cyclization, which I am going to talk about when I talk about the radical intramolecular reaction. So here what is going to happen, if you have a carbonyl group here, if you have a ketone and a ester, that ester can also combine with the samarium. So the important part is that is kind of keeping both this ester and this oxygen in the same site. And now this radical going to participate in a 5-exo trig cyclization, okay, to get to this product. And if you see here, the important part is here, once the radical is adding here, this methyl group which is here and the newly formed methyl group actually going to be down, because going to be in the same site. That is the important thing. Both the methyl will be in the same site, okay. And then you can see this corresponding ester and this corresponding oxygen, the OH which is going to form are also in the same site, okay, because of the chelation with the samarium. So here what is happening, first there is a reduction and then a intramolecular cyclization. So now what is going to happen, it is going to participate in a pinnacle reaction. So first, so it is an intramolecular pinnacle reaction happening. How this reaction is taking place, that first thing is you can see there is a aldehyde and there is a ketone. So aldehyde is getting reduced with the samarium, and now it can go for one round of reduction of this, or it can, okay, so it can either add here, or the samarium can able to reduce this carbonyl group. The ketone can be reduced with the samarium to generate a radical species here which can recombine to form this product. Again, the important fact is you can see this oxygen and this oxygen will be on the, so these two OH are on the same site, okay. So there is another example here of the pinnacle reaction. Now the important thing is you have again a carbonyl compound. So there are two different carbonyl compound here. As I said, what is happening at the beginning. So this is forming a radical species here. So it is forming this samarium ketyl radical, and then it is going to go for another round of reduction of this carbonyl species to generate another round of ketyl radical here, and this double bond will be vanished. So then samarium will make a coordination. So there could be once the samarium will coordinate, now these two ketyl radical go for radical recombination to form this 6-member product. And here you can see that both the OH as the samarium is coordinating with this both oxygen, it is going to be in the same site, okay. So they are actually little in the down. You can see in this molecule there is methyl in the up, both the oxygen is down in the product. There is another example of the intramolecular pinnacle reaction. Here you can see there is a generation of a radical. In this species there is a aldehyde here which is generating a radical, and then there is another carbonyl species here which at the end forming this pinnacle, okay. Again, as I said, both the OH will be in the same site. So again in this reaction you need a more, I think they have used a 10 equivalent of HMPA with the samarium iodide for this reaction to happen, for this reaction to happen. So these actually these also depend on the substrates as well. So I talk about, I think in the previous slide there is a intramolecular reaction that once you form this samarium ketyl radical, if you have a olefin, then it can add there, and if you have a olefin with electron withdrawing group, then also it is going to add, because you can see so this is a radical which will be a nucleophilic radical which will add here with a electron withdrawing group to make this radical species. Then another samarium iodide going to come into the picture, form this samarium species, and it can take a proton from a proton source to get to this corresponding product. So what is happening here, literally you are this carbonyl group is converting to the corresponding alcohol, and it is going to take part some sort of a 1,4 addition to this electron withdrawing group. So what is happening here? You start with this corresponding ketone, formation of this samarium with the ketal radical here, which will generate here, and now it will going to take part in the radical radical addition here, and then what is going to happen? There will be a samarium iodide going to come and then form this type of intermediate species, which what is going to happen? You can see here there is oxygen with the samarium, so there is some sort of a negative character, and there is a ester here, so which is going to recombine to form this product. It is going to form some sort of a lactone here. And then there is another example here. If you have, so again these are intermolecular example. You have a ester and you have a carbonyl group with a so you have a alpha hydroxy carbonyl group. If you have a alpha hydroxy carbonyl group, again this hydroxy kind of act as a directing group here. So this the samarium going to bound and form this type of species first, and now what is going to happen? It can form this type of ketal radical here, and this ketal radical now it is going to add here to this alpha beta unsaturated compound. Okay. Now you can see here finally in the product. So if you see so these two have actually these two oxygen in the same site, this OH, and then it is going to now add to this ester. So it is going to add here first, and then now at the end this alcohol which is going to form, it is going to form a lactone by reacting with the ester. And here the methanol was used as a protic acid, like which can give a proton source. Then there another interesting example here, you can see there is a indole where C3 position there is a electron withdrawing group. Now if you can see there is a there is a carbonyl group here and some sort of a amide groups here. So of course the carbonyl group going to be participate in the reduction in presence of samarium iodide, going to form this type of ketal samarium species, which is going to take part in the 1,4 addition here. So it is going to add to the corresponding indole in the C2 position. So it is going to add here, form this species. Again now it is going to it is going to form this species here, and then what is going to happen? You can see now this has a some sort of enolate character. If you use a corresponding alkyl allylic bromide, it can trap the allyl group here to form this. Now it can form, you can see you have a quaternary center here, you have a you have a tertiary center here, you have a quaternary center here. It forms so because you can see here, as you can see this you have a samarium here which is forming at the beginning, then it is going to take the allyl bromide here to get to this corresponding product here. I have talked about some of the radical cyclization. So now what is going to happen here, from the Rx you are going to generate R dot, which I already mentioned at the beginning, and now what is going to happen, that can take part in a radical cyclization reaction. Here first this carbon iodine bond is getting cleaved in presence of the samarium, and now it is going to add to this corresponding double bond here, and it is going to generate this radical species. And once the radical going to form here, what is going to happen? It can form this, it can take a samarium iodide, form this this species. Now if you have a acetone in the reaction, what is going to happen? The acetone is also going to end up forming that the corresponding ketal radical, correct, which can able to for a so there will be a radical recombination going to happen between these two, so that can form this this product. Okay. So now there is a reaction where I talk about the reaction of the radical species to the corresponding alkene, correct. Here I am going to talk about a reaction where you have samarium iodide and HMPA. Again I mentioned that what is the the role of HMPA. It is going to coordinate, first it is going to the dissociate the THF samarium complex, and then it is going to coordinate with samarium and then change the redox potential. And also I talk about that if you have a carbon bromine bond, then it is going to form the corresponding radical very fast, correct. You have seen that the reaction depends if you have a chloro versus bromo versus iodo. Now once you form this corresponding radical, what is going to happen here? So now you are generating this radical species in this position. So there is two different type of cyclization can happen. It can either go for some sort of a exo decyclization, or it can go for so it can be a 5 exo or it could be a 6 endo. And you can see this will be more favorable compared to others. So that's how it is going to end up adding here, and that's going to generate a radical species here, a samarium species, okay, which can able to take a proton, or it can go for a hydrogen atom abstraction to get to this product. So now I am going to talk about some of the Grignard reactions here that you have learned about, that if you have a corresponding alkyl iodide and if you have a samarium iodide, it is forming this radical species, and then the samarium iodide can comes in and forms the corresponding some sort of a R. So you will end up making some sort of a samarium I2 species going to form. Now if you can consider some sort of very similar to some sort of a Grignard type of reagent. Now you have a anionic character here which can add to this corresponding carbon group here. Once you add here, you end up making to these corresponding alcohols. Again there is this Barbier reaction here. I explained during the Barbier reaction that if you make samarium, as I was telling you, that methyl iodide and samarium iodide going to make this methyl samarium species, and which is going to now add to this species through the bottom phase, because the top phase is hindered because of these methyl groups. So that's why it is end up forming this product as a major product. There is another example of the Barbier reaction here. So what is happening here, you can see in this starting material to product. Let's try to understand what is happening here. If you see, this carbon sulfur bond is getting cleaved, because, and then we are seeing this particular group is getting into the system. So what is happening again, if you see the samarium iodide going to form some sort of a first it will cleave this bond and form the corresponding. So very similar to the carbon iodine bond, it is going to cleave this carbon sulfur bond to generate a samarium species from here. It will generate a samarium species. So it will generate a radical first, and then it will generate a samarium species after the reaction with samarium iodide. And now this samarium iodide can able to act as a Barbier reaction to react with the corresponding carbonyl group here to get to this product. There is another example for an intramolecular reaction happening here. So in this reaction, what is happening, you can think about that samarium iodide is cleaving this bond, forming this corresponding the samarium species here. So it can form the the radical, then the samarium species, which can now able to add to this corresponding carbonyl group here. And once it is adding to the carbonyl group, you can see it is going through some sort of a tangent state here, and then it is forming this corresponding alcohol. So the important thing is, once you have this other carbonyl group which could be ester, then that is the samarium is going to bind with that in the corresponding tangent state, making sure these two oxygen will be in the same side. So this OH and the carbonyl group will be in the same side. So that will be the product in the reaction after taking a proton. Another example here, forming a samarium species first with the corresponding iodo, and then it can participate. So there are, you can see it can react with the ester also. It is not only reacting with the corresponding aldehyde or ketone, it can react with the ester, and then there will be this OET going to get out to form this carbonyl species. Here what is going to happen, you have this corresponding chloride here. Now this corresponding chloride can also going to form a samarium species in case of samarium iodide, and that can also going to add here. Okay, so it can add to this type of carbonyl group here. And once you can see, if you think about this phenyl is off, if you think this phenyl is off, the addition of this nucleophile is going to happen from the bottom phase. So it is going to come back, after it's forming the samarium species, it can form through the bottom phase, and it can going to form this, you can see now this OH is going to form the off. So this OH and phenyl will be on the same side, because the nucleophile is attacking from the bottom phase. Another important example here, so these are a type of a Reformatsky reaction happening because you have a compound which has a alpha bromo esters are present here. So now if you use a samarium iodide, what is happening here? Now you can see from this type of mechanistic drawing, first there will be cleavage of this carbon bromine bond, and it will going to generate is this corresponding samarium species there. And now what is going to happen, that corresponding the samarium species going to add to this corresponding carbon group. So it will form this corresponding samarium here, and then it is going to connect here, and then this is going to add here to this corresponding carbon group to form the alcohol. Okay. So it is some sort of Reformatsky reaction. We have learned about Reformatsky reaction using the zinc, but here we are using the samarium for the same transformation as well. There are several different type of other reaction also. I am just going to talk about the another important reaction is aldol reaction. What is the aldol reaction? If you remember, the aldol reaction, you end up synthesis of beta hydroxy carbonyl compound. Okay, this is alpha beta. So now what is happening, by using this samarium iodide chemistry, we can also able to make a beta hydroxy carbonyl compound. So let's learn how this reaction is happening. Okay. So again, if you know that if you have a carbonyl group here, it can form this corresponding ketyl radical, and once it is forming the ketyl radical, that means what is going to happen, you make this radical here and a samarium species here. So now if you have this species here, what is going to happen, now that can participate in two different ways. It can go for finally convert to the corresponding anion, and then it can add to this epoxide. Now if you see in this epoxide, you have this carbonyl group. So means that position will be more electrophilic compared to the other position. So that's why the nucleophile going to attack here. Okay. So it is going to form an anion here, and some sort of a Barbier type reaction going to it's going to add to the epoxide to form this corresponding product here. And again you can see here this, if you see in this reaction, in this particular position you end up forming this H here. That means so this will be attacking from the position from the bottom face of this to form this corresponding product. Okay. So you end up again forming this beta hydroxy carbon compound here. So in this part I talk about samarium iodide generation, how you generate samarium iodide from starting from this the 1,2-diiodoethane using samarium. Then I talk about pinnacle reaction, different type of pinnacle reaction. It could be intramolecular or the intermolecular. Then there are the ketone aldehyde reduction reaction, intramolecular cyclisation reaction to the olefin and alkyne. Then there are the Barbier reaction and the Reformatsky reaction, also the aldol reaction. So I think these are the important reference if you want to learn about the samarium chemistry more. And again, thank you for coming to the class, and I am going to see you guys in the next class. Thank you.